All right, so in the previous video we talked about the Born-Lambda equation and the Born-Meyer equation, and we talked about how to calculate lattice energy using that. Now we're going to cover something called the Kapustinski approximation. Okay, so for the Kapustinski approximation, this is just an approximation, okay? It has more error than the Born-Lambda equation, and part of the reason for that is you use this only when the lattice structure type is unknown. So definitely if you know the lattice structure type, you're going to want to use the Born-Lambda equation, okay? Because if we know the lattice structure type, we can get the Madelung constant. Notice the Kapustinski approximation doesn't use the Madelung constant. It actually doesn't use the Born exponent either. Which makes this equation a little bit simpler to use because you don't have to determine a Madelung constant, you don't have to determine a Born exponent, but that makes this equation more error prone. And you only use this when the lattice structure type is unknown. But it's going to have more error generally than the Born-Lambda or Born-Meyer equations. But this is the equation that you'll use. All right, so we are going to ultimately look at a problem and see how you use the Kapustinski approximation. All right. So it's an approximation, that's all it is. So what we're going to do is do the same problem. We want to assume a rock salt structure for rubidium bromide. This is what we did in the previous video. We want to use the Kapustinski approximation and see if we get something relatively similar. All right, so let me go to the paintbrush and I'm going to go ahead and do this. I'm going to erase this part, erase that part. This was, by the way, the lattice energy that we got in the previous video using the Born-Lambda equation. So what I'm going to do here is I'm going to, I'm going to leave that right there. So let me do that. All right. This down here is the Kapustinski equation, or approximation I should say, because it is an approximation. And you don't see it over here, but this is U naught, this is the lattice energy. So let's go ahead and calculate the lattice energy. And one of the nice things about this is that we actually technically already have the interionic distance calculated because it's the same problem. It's for rubidium bromide. We calculated that in the previous video, and I'll show you again in this video how to do it just so it's clear. Now notice there's a few differences here. We don't have the Madelung constant, we don't have the Born exponent, but what we do have is V and the two charges. Let's go ahead and calculate interionic distance again. So the interionic distance is approximated as the radius of the cation plus the radius of the anion in the lattice. And for rubidium bromide, now this is something I looked up in a table, but I found that the radius of rubidium was 265 picometers. We add on to that the radius of bromide, the anion, which is about 94 picometers. And when we summed those together, we got about 359 picometers. And I'm going to do it again, even though it's a little redundant. I'm going to show you how to convert picometers to angstroms. You can either memorize the conversion factor, which I don't recommend because you can get them mixed up pretty easily, but you should understand where the conversion factor comes from. 359 picometers, I want to convert that to angstroms. And the reason I want to do that is because for both the Born-Lambda equation and the Kapustinski approximation, you have to put the distance in angstroms for that equation to work out. So I'm going to say, well, remember that milli is 10 to the third, micros 10 to the sixth, nanos 10 to the ninth, picos 10 to the 12th. So I know there are 10 to the 12th picometers in 1 meter. I also know that 1 meter is 10 to the 10th angstroms. So that ultimately means I'm going to divide the number of picometers by 100, and I get that this is going to be about 3.59 angstroms. And that's exactly what I got here. That's my D naught. Okay, that's the D naught I'm going to use in the Kapustinski approximation. All right, so what I'm going to get is my U naught is equal to 1,202. I'm going to multiply that times V. What V is it is the number of ions in a unit formula. All right, so we're dealing with rubidium bromide. There's just one of each because they both have a charge with magnitude 1, plus 1 and minus 1. So the number of ions is going to be 2, all right? Charge on one is plus 1, the charge on the other is minus 1. And we're going to divide that by 3.59 angstroms. Then we're going to multiply that times the quantity 1 minus 0.345 divided again by D naught, which is going to be 3.59. All right, so let's go ahead and calculate that. All right, I'm going to take first 1 minus the quantity, 0.345, divided by 3.59. All right, and then I'm going to multiply by 1,202 times 2 times minus 1 divided by 3.59. And let me write down the answer over here. All right, so I got that the lattice energy from the Kapustinski approximation is about negative 605.3. And that's going to give it to me in units of kilojoules per mole. Let me get the toolbox out and I'm going to box that. Let me do it in a slightly different color. Let me do light blue. This is the lattice energy, but this is from the Kapustinski approximation. All right, so notice when I did the Born-Lambda equation, I got negative 609.4, and with Kapustinski approximation, negative 605.3. Those are pretty close. So the Kapustinski approximation does have more error in it, but it's still, if you don't know the lattice type, it's a good approximation. Okay, and that's how you use the Kapustinski equation ultimately to calculate. It's how you calculate the lattice energy. And like I mentioned in one of the previous videos, a lot of times what we don't just want to calculate lattice energy using this. What we want to calculate is the thermodynamic radius. And that's going to be the topic of the next video. So it turns out that thermodynamic radii are really good to calculate because sometimes that's actually what we don't know. We don't know the thermodynamic radius, okay? And the reason sometimes we don't know the thermodynamic radius is we don't have simple compounds like rubidium bromide. Sometimes we have something in here, like in this equation, or this problem, excuse me, we have an anion that's C2 2-. What is that? I mean, can you really look up the radius of that with respect to calcium? No, you can't. So sometimes just if we had simple cation and a simple anion, we can just add them together and get a good approximation. But sometimes we actually just want to calculate the interionic radius, not the lattice energy, because we can determine the lattice energy from a Born-Haber cycle, and then we can use that to calculate d naught. Okay, so we're gonna ultimately calculate. We're gonna calculate the equilibrium interionic distance in the next video. So join us next time. Make sure to like this video and subscribe to the channel for future videos and notifications. Thank you.